So, hello everyone. Thank you for being here. If you get tired of me, feel free to walk out. There are not enough seats here. So, cool. I'll be talking about end-to-end testing at Facebook, in particular how we've made our tests readable, stable, and maintainable. Cool. So, I work for the end-to-end automation team at Facebook London. My name is Archit Sachdeva. That's the way you pronounce it. So, yeah. Our team is responsible for maintaining the infrastructure and frameworks to run end-to-end tests at Facebook. And we've been presenting at SeleniumCon for the last 2 years. 2 years ago, Remy talked about mobile testing at scale. And last year, Lawrence spoke in London about iOS end-to-end testing. Both these talks are available on YouTube, so feel free to check them out. Let's get into what we're talking this year about. So an outline, it's going to be straightforward. We'll begin with what a typical end-to-end test at Facebook is. Then we'll get to why Facebook invests in end-to-end tests. And finally, we get to how we'll solve problems regarding those end-to-end tests, which we'll run into. So let's begin with what. So how many people here are invested in end-to-end testing? A show of hands. That's almost all of the room. But end-to-end tests can mean different things slightly for everyone else. So at Facebook, Facebook end-to-end tests mean what tend to mimic how people tend to use Facebook. So several years ago, Facebook was a website. And most of our users were using facebook.com through a browser. And then our tests used to be just WebDriver test against facebook.com on a remote browser. But today, Facebook is a suite of apps. We have Facebook, Messenger, Instagram, and Workplace, to name a few. And the way people use these apps has changed. They use them on the browser, but more prominently on their phones throughout the day. So our end-to-end tests reflect that change, and now our test suite constitute end-to-end tests on the browser and on applications as well, on a remote simulator and emulator. So what's an example of a test? Say for Messenger, a test would be getting a remote emulator, installing the app, launching the app, logging in as a test user, searching for a friend of that test user, sending her a message, and validating that the message was sent through the UI. So that's what end-to-end tests in our world mean. Then we get to why we invest in them. I guess all of you invest in end-to-end tests, so you have your own reasons. But to sum it up in one word, it would be coverage. You can cover code across your entire stack and get good coverage out of a single end-to-end test. But at Facebook, this coverage means something for us. The fact end-to-end tests give us huge coverage allows us to release code rapidly. If you learned, we recently started pushing our website, facebook.com, every couple of hours. And what this means from an end-to-end test point of view is that if we have a set of critical end-to-end tests, and if any of them fails during the push, we stop the push. Cool. So if you're interested in our rapid release cycle, you can read up more about it at code.facebook.com. The next reason we invest in end-to-end tests is our culture. At Facebook, engineers write their own tests. They are responsible for their code. We follow a model of test ownership. So we want to give developers the tools they want to write tests as they see fit for their product. So we want to enable developers to write end-to-end tests, because that's in our culture. And do developers want to write end-to-end tests? The answer is yes. As you can see by the growth in end-to-end test here, we have had a huge growth in the last 2 years. So giving developers the tools to write end-to-end tests will lead them to write more tests. Let's summarize what's good about end-to-end tests. It's coverage, it mimics real-world usage, and it gives us confidence for our release. But with everything good, there are trade-offs. So let's talk about the flip side of good, the bad. The first one is execution speed. Tests tend to be long by their nature because they're end-to-end and they're performing UI interactions. But they also require huge setup costs, right? Like if you want to test the Messenger app on an emulator, you want to boot that emulator, install the app, and so on. So tests require huge setup, which plays a role in their execution speed as well. Next is hard to read and write. WebDriver is a remote interface protocol and not a protocol to write tests exactly. So for a complicated UI, writing a WebDriver test gets pretty complicated. And if you're not the test author, understanding what's going on becomes very hard. And lastly, it's stability. End-to-end tests are flaky is a common refrain we hear, and flakiness is a keyword in many talks. Cool. So this is what the final and the meaty section of the talk is going to be about, is that how we solve these problems. So let's begin with execution speed. As we just discussed, execution speed has the bottleneck of setup. You want to get, if you want to test against a test on iOS with a remote simulator, you want to, if you want to test an application on iOS, you'll probably need to boot up the simulator, install the app, and launch the app. But what if the test, even before it starts executing, could get a simulator with the app installed? At Facebook, we built a project called OneWorld, which gives us runtimes as a service. This has several wins for end-to-end testing. To begin with, you get simulators and emulators waiting on tests. Even before a test starts, it can request, hey, give me a simulator with Messenger installed on it, and it would get one, and then the test would start. This also gives us pre-test setup. The installation and booting up WebDriver agent in case of iOS and Selenium in case of Android. And this also allows us to speed up by parallelizing the test build and the application under test build. Thirdly, health checks. Stuff could go wrong when you boot a simulator or try to install an application. There might not be enough space on your emulator, for instance. OneWorld gives us health checks so that we always get fresh and clean simulators and emulators. And lastly, we get post-test metadata. This allows us to see if something went wrong during the test. So for example, this would give us the video of what happened during the test, application logs, element trees, and system logs. So if you're interested in OneWorld and want to read more about it, you can check out our post at code.facebook.com as well. Good. The next problem we want to tackle is that the tests are hard to read and write. What do I mean by this? Let's look at an example for what might the code be in a raw WebDriver test. Pretty solid code. We want to find an element feed, find a sub-element permalink inside it, and pick the third one, click on it, and find some other element after that. But this won't work in practice, right? Like finding an element immediately after a click. Someone would realize this test is flaky and add a sleep. How many of you seen a post on Stack Overflow saying, hey, if your test is flaky, just add a sleep? And then you realize sometimes 2 seconds won't be enough, so let's add another sleep. And we started seeing this across our tests. And the next one is pretty good. OK, that didn't work, sorry. Yep, sometimes you need to click twice if you get that. If you've seen, we've seen certain examples where people just do this for some reason. And at this point, I'm not even sure what you're testing, right? Like, are you sure the first click is not supposed to work? And then certain times the feed would be slow to load for some infra reason. And then you want to make sure you find the feed. So let's just do a while loop until we find it, right? Like, what's wrong with this? If the test is failing, it's just going to sit there, right? Like, you would get nothing after the test ends. So a lot of these problems are actually solved by the wait until abstraction WebDriver gives us. But now the code is getting already hard to read. And you don't want to do checks like is enabled within your code base, right? And there are still possibilities of having flakiness later on. So our goal was to build a declarative API which would express intention. And the way we did it is by learning from the page objects design pattern the community built and taking it further with the notion of reusable and nestable components. So now I'll be diving into some code, but before that, let's go through the key concepts I would like you to know about. So the first one would be locators. They are just identifiers for how you find web elements. You must be familiar with them if you use WebDriver. So they could be the raw identifier or the tag name or a class name and so on. Then we built a tree of these locators. It's what we call a UI definition. It's supposed to model a piece of UI on your web page or in your application. And once we take this UI definition and add semantic actions to them, we call it a component. This component is a concrete representation of something your page actually does. So it could be if you have a form, you can have a component for it, and you could have actions which would be like fill in the form and submit it. And lastly, page objects are very simple in this model. It is a representation of a concrete page, and we define it by having a set of initial components we expect to be present on the screen when the page is loaded, and an optional URL in case you want to navigate to it directly. Cool. So let's walk through an example. What's a classic reusable piece of UI on Facebook? It's got to be a post, right? OK, that's a math reference. I don't see a math audience here, but all right. So a feed story is a reusable piece of component. So let's try to model this as a component. So we'll begin with a class feed story. Let's keep it empty for now. And as I defined earlier, a component is just a UI definition plus some actions. And a UI definition is a tree of locators. And to begin the tree, we need a node, which I've marked here in blue. So that would be the container of this component. So let's add a definition which just has a container. And the locator could be anything, like we don't care about it. But we're going to give it an optional name. In this case, story. This is an arbitrary string we pick to decouple the locator and the actual view hierarchy. But so once we add a definition, this is now a component with 0 actions. So feed story now conforms to being a component. But this is pretty useless right now, right? Like you want to perform actions like clicking on Firma's photo. So let's try to encapsulate his photo within this component. The photo here is in green. And to encapsulate it, we have an API to the root, which would be adding a descendant. So we simply add a descendant and assign it a name again. And this name is of our choosing. We pick the name profile photo because it is a friendly name, which we can refer to it later on. And similarly, we might want to model the permalink to open the post in a new page. So the permalink here in red, we can add a descendant for it. And similarly, we can do the same for the actual content of the post. So once we add all these descendants, we can start building actions on top of this. So what might be an action we want to do on a feed story? Well, it could be getting the actual post content of the story, right? So let's define a method which does that. And the way we do that is through a method called getTextOf, which is defined in component. And we refer to the node we want to get text of through the actual name we have passed. This decouples the locator and the actual action. And this method is, again, very semantic. It just says, hey, get post text. So it's going to get the text of the post. And similarly, we can have an action to open the profile of Firma here. So here we would just say click and go to. Again, we want to have everything semantic, so we don't want void methods here. So we say this would end up on a page object called user profile. So how does a component look like at the end of the day? It looks like a definition with predefined methods on it, which have associated semantics. But as we all know, like these are somewhat common actions, but the most popular ones are liking and commenting, right? But I haven't defined them in yet. And the reason for that is like and comment are pretty common piece of UI in Facebook itself, right? They're reused across photos and events and so on. So we want to probably encapsulate that in its own component because we might want to reuse it somewhere else. So let's define a class story footer. It would be pretty simple. It would just have 2 descendants called like and comment. And we can just add the definition and define methods to like the post or open the comment dialog box, which tapping on comment would do. And once we have that story footer, as you can see, this has a concrete definition. And a definition is just a tree of locators, right? So we can probably take this component and nest it inside this feed story we just defined. So we have a method with descendant which can actually take in a component, and it's typed. And after we add that descendant, the definition is now updated to encapsulate the story footer here. And from within that component, we can also get access to liking and commenting by having a method which would just get the story footer within that component. And it's all typed. We get a typed story footer instance, and which would have the methods we just defined on it. So eventually, we can build on feed story, and it would have semantics like this: get the text of the post, open profile, open post, get author name, and get story footer. All of these are typed. And this builds on the pattern of page objects, but enforces it by everyone. And this also brings us the nice definition of nested components. It allows you to nest one component into another. So once we can do that once, like, we have to go deeper, right? And the feed story is just a part of the entire feed. So we can build up components by reusing already built components. So once we have the class feed, we can say, hey, this has to have a container, and then we can add a already known descendant, which is feed story. So let's add a definition. Once we have the definition, we again have conformance to being a component. Good. Then we can start looking at further descendants. So the inline status composer here is going to be another nested components inside it. We could have any definition for it, so let's add a definition. Let's add a descendant for that. So on the feed, we could have semantics like this. Open the composer, open self-profile, get the top story. I want to focus on the last one, which is scroll down to feed story to Boolean to feed story. If you are into Haskell, you know what this means. So we take a predicate, which is going to be a method from feed story to a Boolean. And at the end, we return a feed story which satisfies this. So as an example, you can scroll down until you find a post which matches certain text, or scroll down until you find a certain post authored by Sophie Germain. And all of this is again typed. The method author would be defined in the class feed story. This allows you to have semantics throughout and have very readable code. So the code here just reads feed.scrolldown to story.author. It's like fairly straightforward and returns a typed instance again. This brings us finally to page objects. So page objects are very simple. They're supposed to be model of the entire screen. Here we already have the feed component here, and we have the search bar at the top. We can add that, and the tab bar at the bottom. So a page object is just a set of initial components we expect to be present on the screen. So in this case, it would be the search bar, the feed, and the tab bar. And as soon as you add the field initial components to this class, you can say this is now a page object. And we say a page object is loaded when all the initial components are present on the screen. If you want to navigate to a page object directly, you can optionally add a URL. If you want to test a certain feature, you can add a deep link to within your application or a URL for a web page. And from within a page object, we can have semantics like getting internal components. So here we can have methods like get search bar, which would give you a search bar, and then you can access methods inside the search bar. So how does a test look like in this world? Well, this is what a test looks like. So you begin with waiting for login screen, which is going to be a page object, and then you have a method defined on it, which would log in as a user. You can select a composer, open it, enter some text, post it, and then select a story which contains that text, open a permalink, and then post a comment. All of this is fairly readable and understandable, right? And all of these instances are typed. You can see the return type of each line at the right side here. So what developers can do is define the right semantics, and then start having just autocomplete their test once those semantics are defined. So what wins did we get out of this? Better readability, as we just saw. Hiding the underlying WebDriver calls makes your test highly readable. Second, it's easier to maintain tests. If something, the decoupling between the components and its locators and the names we give the descendants and the semantics we define on it, make it very easy to maintain those tests. And lastly, as we've seen by the growth, it's very easy to write the next test once you've written the first one. So the cost of writing a test goes down with time. So this brings us to the final problem we had, which is stability. So we use WebDriver-like protocols for everything under the hood for all of this. So because we use that, we go through remote web elements. And as you all know, remote web elements are the root cause for stale element references, right? Everything I just defined never goes through remote web elements. So we've basically fixed this for inside Facebook. We never see stale element references as a root cause of test failures. So the underlying principle which allows us to do all of this is the principle of no surprises. The developer should write what is expected on the screen and let the framework take care of everything else. So let's go through another example to explain what I mean here. Say you want to open Firma's profile again, and you want to do it through WebDriver directly. So you would say find some stories and loop through them. And as soon as you're looping through stories, you're basically done for, since the UI might refresh as you're looping through, and you could end up with a stale element reference anywhere within there. And this would even be a problem if your UI loaded asynchronously, which is often the case for large mobile applications and websites as well. So how does the same code look within our abstractions? It looks something like this. We just say, hey, select the unique feed story, which satisfies this predicate, and open a profile. And as you can see, we never go through remote web element calls here. The framework does all the hard work for you to requery the UI when anything goes wrong. So to summarize, how does this work? A component is matched entirely before we perform any actions. We would ensure all their descendants are present before doing any action. Secondly, uniqueness is guaranteed. As the method we just described said, select unique, we ensure developers know what they're doing and ask them to be very strict about their tests. So we want to guarantee uniqueness. And lastly, we automatically requery if the UI refreshes anywhere. So what wins do we get out of this? All the bad patterns we saw. No sleeps, no repeated statement, no while loops, no waits within the test. The developers no longer need to write this. Everything is taken care of by the framework. Secondly, a minor win, but we see no XPath within our locator abstractions. As you've seen, XPath is quite complicated to use, and you need to teach a new person onboarding each time. So the UI definition, because it's just a tree of locators with descendants defined on it, you never need to actually go through XPath, and you can have simple locators like ID or tag name. And lastly, as we just discussed, no stale element references at all. So let's summarize how we fix the bad part. Execution speed. We request resources through one word. We would request a simulator or an emulator or a browser and run the test against it. This allows us to parallelize stuff. Secondly, we discussed how end-to-end tests are hard to read and write. We built a declarative API which enforces semantics by developers for it. And thirdly was stability. The same APIs are very stable in the sense they allow requery within the context of the component. So the overall summary of the talk: correctness tests against what are end-to-end tests for us? They are correctness tests against applications and websites for us. Why do we use them? Coverage, release process, and our culture of test ownership. And how did we fix them? How did we fix all the issues we had with end-to-end tests, declarative and stable APIs, and requesting resources? So that's the summary of this talk. And a lot of us from Facebook are here today: Dimitri, Marcelo, Graham, Luke, and me. Marcelo might be giving a lightning talk about accessibility in Android with Selenium. So do check that out. With that, thank you very much.